Good morning. In this lecture, we will discuss about the work done during an isothermal process. Isothermal process is a process in which the temperature of the system is constant throughout the entire process. Consider a 1 kilogram of a perfect gas be allowed to expand very gradually under isothermal conditions. Let the initial and final state be represented by A and B on this indicator diagram or the PV diagram. The PV diagram means pressure is on the y axis and the volume is on the x axis. A system is in a state A represented by the pressure P1 and volume V1, and it changes to the another state B represented by P2 and V2. When it changes from state A to B, the system is having the same temperature, or the temperature of the system remains constant when it changes from A to B, then that process is called an isothermal process. Now the work done to change the system from the state A to the state B is given by W is equal to integral A to B dW, which is equal to integral V1 to V2 P dV, which we know that this is equal to the area under the curve AB. Now we are considering a perfect gas. So for a perfect gas, we know that PV is equal to nRT, where P is the pressure, V is the volume, N is the number of moles present, and R is the universal gas constant whose value is 8.314 joule per mole Kelvin, and T is the temperature. This quantity N into R, number of moles into universal gas constant, usually represented by the small r. So this equation can be written as PV is equal to RT. Now from this equation, the pressure P is given by RT by V. So substitute this RT by V in the expression for the work done to calculate it. So W is equal to integral V1 to V2 P dV, which is equal to, instead of P we can use RT by V into dV, which is equal to R is a constant, we can take it outside. The process is an isothermal process, so the temperature is also constant, so we can take it outside, so that remains is integral V1 to V2 1 by V dV. The integral of 1 by V is nothing but the log V, so it will be RT log V from V1 to V2, which is equal to RT log V2 minus log V1. But log A minus log B is log A by B, so this equation can be written as RT log V2 by V1. So usually in thermodynamics we will use the common logarithm, not the natural logarithm. So we will convert it into common log, that is base to 10. So this equation will be 2.303 RT log V2 by V1. So this is the work done on a perfect gas when it undergoes an isothermal change in its state from one state to the another, having the volume V1 to V2. Or if we are taking 1 mole of this substance, then small r will be capital R, So in that case W can be written as 2.303 RT log V2 by V1. So this equation actually represents when 1 mole of a perfect gas undergoes a change in its volume from V1 to V2 under isothermal conditions. That means the isothermal processes can only be brought about when the system under steady is in good thermal contact with the surrounding. So whatever heat is generated, that has to be given out to the surrounding, or whatever heat is lost will be absorbed from the surrounding to keep the temperature constant throughout the process. Then only the system will undergo the isothermal process. So this is the work done during an isothermal process. Now let's see what is the corresponding expression for the work during an adiabatic process. An adiabatic process is a process in which no exchange of heat takes place. So we are going to discuss about the work done in an adiabatic process. So during an adiabatic process, no exchange of heat, more specifically heat and matter, takes place between the system and surrounding. The system under consideration is kept perfectly thermally isolated from any other system or the surrounding. Further, the change from one state to another should be very rapid so that chances of heat leakage be minimum. Now again consider a 1 kilogram of a perfect gas which undergoes an adiabatic expansion from the initial state A having the pressure P1 and volume V1 to the state B having the pressure P2 and the volume V2. During this process, the temperature of the system changes from T1 to T2. If the temperature remains same, it will be an isothermal process, but during an adiabatic process, since there is no heat exchange takes place between the system and the surrounding or system and other systems, then whatever heat is generated during the process will increase the temperature of the system, or whatever heat is lost during the process will cool down the system or decrease the temperature of the system. So there is a change in temperature during an adiabatic process. The important thing regarding an adiabatic process is that it is a very rapid process. So to calculate the work done during the process when the system changes from its state represented by the A, state A having the pressure P1, volume V1 and temperature T1, to another state represented by B having the pressure P2, volume V2 and temperature T2 through an adiabatic process, then work done is equal to, as usual, it is P dV from initial volume to the final volume. Now we have to consider the equation of state for an adiabatic process that we will discuss later while discussing the first law of thermodynamics, but here I am taking that expression that is familiar to you, that is for an adiabatic process PV raised to gamma is equal to a constant, let's call it as K. It is actually called Poisson's law. So which is equal to integral v1 to v2 p, we can write it as k by v raised to gamma into dv, which is equal to k into integral v1 to v2 1 by v raised to gamma dv, which is equal to k into, that is v raised to minus gamma. The integral of v raised to minus gamma is v raised to minus gamma plus 1 divided by minus gamma plus 1 from v1 to v2, which is equal to k into v2 raised to 1 minus gamma divided by 1 minus gamma minus v1 raised to 1 minus gamma divided by 1 minus gamma. So this is equal to, we can take this 1 minus gamma outside, so 1 minus gamma into k into v2 raised to 1 minus gamma minus k into v1 raised to 1 minus gamma. This is equal to 1 by 1 minus gamma into, if I am multiplying and dividing first term by v2, the numerator become k into v2 raised to gamma you can write the first term like this, k into v2 raised to 1 is v2 divided by minus gamma is v2 raised to gamma minus v1 raised to 1 minus gamma, I can write like this, k into v1 raised to 1 divided by v1 raised to gamma. But k by v raised to gamma is p, so k by v2 raised to gamma is p2. So this equation become 1 by 1 minus gamma into k by v2 raised to gamma is p2 v2 minus k by v1 raised to gamma is p1 into v1. Or this equation can be written like this. We can take a minus sign from here or multiply throughout by a minus. We will get 1 divided by gamma minus 1 into p1 v1 minus p2 v2. This is the expression for the work done during an adiabatic process. So the work done during an adiabatic process of a perfect gas is given by W is equal to 1 divided by gamma minus 1 into P1 V1 minus P2 V2. Now we can express it in terms of temperature also. That is, for a perfect gas we know that P1 V1 is equal to RT1 and P2 V2 is equal to RT2. So this equation can be written as W is equal to 1 by gamma minus 1 into P1 V1 is RT1 and P2 V2 is RT2. So this R can be taken outside, R into T1 minus T2. So R T1 minus T2 divided by gamma minus 1 is the another expression for work done. So which is equal to small r is n into r divided by gamma minus 1 into T1 minus T2 is the another expression for the work done during an adiabatic process. Since in an adiabatic process no heat is allowed to enter or leave the system, the external work W is done by the gas at the expense of its own internal energy. So during an adiabatic process, its internal energy of the system decreases. We will discuss what the internal energy is all about, but just remember here is that the work is done by a system during an adiabatic process at the expense of its internal energy. Now we have to discuss about the work done during an isobaric process. Isobaric process means the pressure of the system remains constant. So, a process in which the pressure of the system remains constant throughout the process is called an isobaric process. Now, if you consider the indicator diagram for a isobaric process, you can see that pressure is taken along the y-axis and the volume is along the x-axis. Then pressure is constant means it will be parallel to the x-axis, or we can say that it is a isobaric process is an horizontal line parallel to the x-axis or the volume axis in the PV diagram. The quantity of heat supplied to the system will result in an increase in temperature as well as increase in volume. So that for 1 kilogram of gas, the heat supplied to the system is utilized for increasing the temperature of the system and doing the pressure volume work. So that we will discuss later how this equation comes out to be Cv dt plus Pdv and all. So this is the work done during an isobaric process. Now we have to consider another process, that is the volume remains constant, which is called a isochoric process. So we have to discuss the work done in an isochoric process. Isochoric means the volume remains constant. So the processes in which the volume of the system remains constant is called an isochoric process. It is otherwise called a isomeric process. Now if you consider the PV diagram of a isochoric process, then it will be a vertical line parallel to the pressure axis. So in that case, the work done W is equal to integral P dV. So there is no volume change, it will be always 0. So the work done in an isochoric process is 0. That is, all the heat supplied to the system goes to increase the internal energy, that is temperature of the system. So whatever heat is supplied to the system, delta Q, will be utilized to increase the temperature of the system. Here it will be del Q in a isobaric process is Cp into dt, which is actually used for increasing the internal energy as well as doing the external work. But in the case of an isochoric process, the heat supplied to the system is completely utilized for increasing the internal energy. So that's all about the work done during different thermodynamic processes like adiabatic process, isobaric process, isochoric process and isothermal process. So that's all about this lecture. Thank you.